Okay, welcome to the first theory lunch of the semester. We are very happy to have Shubhangi tell us about polynomials. Before we start, maybe because it's a new year, we should do a quick round of introductions. So, I'm Mark Braverman. I'm a professor here in theory, and my office is over there on the other side.
Ran Raz, I'm also a professor in theory. My office is there at the end of the corridor.
Ilya, I'm also faculty on the other side of the door.
I'm Ramon Van Handel. I guess in theory I'm also a professor. Maybe that's the intended meaning of the word, as opposed to a practice. Nobody's laughing. So it must not be funny. Yeah.
I'm Mateus. I'm a fourth year PhD student working at Weinberg.
I also try to be funny. I'm Bhargav. I'm a first year student with 3 years of experience.
I'm Corey. I'm a second year student working with Bob Sargent. I'm Kunal. I'm a first year grad student.
I'm Gritgon. I'm a first year student.
I'm Matt Weinberg. I'm also faculty here on the other side.
I'm Victor Miller. I work up in the north part of Princeton in a place called CCR.
I'm Linda Cook. I work with Paul Seymour in the math department.
I'm Cleve. I'm studying a PhD working with Volkovich.
I'm Wade. I'm a fourth year PhD student working with SMG.
I'm Danny Chan. I'm a PhD student at third year working with Professor Jennifer Rexburg.
I'm also Wade. Third year PhD student working with Professor Bhargav.
I'm Vijay. I'm a postdoc. My office is over there.
I'm Zach. I'm a fourth year math undergrad.
I'm Tristan Bolner, also undergrad.
Casimir Kotani, undergrad.
I'm Danny. I work at the same place as Victor, and I learned discrete geometry from Shubhangi.
I'm Bhaskar, first year master student working with Mark Andrew.
I'm Hua Chen Yu. I'm a research scholar. My office is in that one.
I'm Manik. I'm a second year student working with Zev.
I'm Ben Lund. I'm a postdoc working with Zev.
I'm Jonathan. I'm a fourth year undergrad in computer science.
I'm Vicky, first year graduate student in computer science.
I'm Eitan, fourth year undergraduate computer science.
I'm Abrar, first year PhD student.
I'm Carlo. I'm second year master's.
I'm Linda. I'm also a second year master working with math.
I'm Yufei. I'm a second year grad student working with Bernard Chatel.
I'm Uma. I'm a second year graduate student working with Andras.
I'm Clay, second year PhD, Matt Weinberg.
I'm Miriam, third year PhD, Matt Weinberg.
My name is Ariel. I'm a fifth year student also working with math.
We stuck I'm not working with math
anymore.
Let's start here non-effective in Approximate.
I'm Bernard Chazelle. You cannot see me because this is big.
Are you working with math?
I'm a first year grad student working with math.
Okay, so welcome if you're new, and welcome to Shubhangi.
Okay, so thanks everyone for coming. Thanks for having me here. I will tell you all about, this is working, yeah? I'll tell you all about the factors of sparse polynomials, and feel free to stop me with questions at any point. Okay, so let me define what I mean by a sparse polynomial. So you're given a polynomial f over some underlying field f, and we're thinking of n-variate polynomials. And let me bound the degree of each variable by a parameter d. So we'll see what we want to set d to be, but I'm not bounding the total degree of the polynomial. Each individual variable, the degree is bounded by d. And the sparsity of a polynomial is just the number of monomials that appear in it. So for instance, that polynomial has sparsity 4. And in general, if each variable has degree bounded by d, the sparsity could be as high as d plus 1 to the n, because the total number of monomials you can have with each variable bounded by degree d is d plus 1 to the n. And when we talk about sparse polynomials, we'll think of polynomials with much fewer monomials than d plus 1 to the n. This, even for small values of d, this is exponentially large. Think of n to be large. So we'll think of sparse polynomials to be roughly maybe polynomially many monomials. And this is the sparsity of a polynomial is natural, well-studied notion. I won't try to motivate it. And the main underlying question we will be looking at is, if you're given a sparse polynomial, are factors of sparse polynomials, are they sparse? So this is what we will try to see. So here are some examples of polynomials, just to understand this question better. So that's a polynomial f. It is an n-variate polynomial, and that's how it looks like. For each variable, you look at xi to the d minus 1, and you take the product of that over all variables. So you get a polynomial in n variables, individual degree is d. Good. What can you say about its factors? How many monomials do they have? And this is, g is a factor of f. Because variable by variable, if you look at xi to the d minus 1, this term is a factor of that term, and then you take the product over all variables. So if you look at how many, so f had 2 to the n monomials when you multiplied it out. G has d to the n monomials. So g is a factor, but it's much denser than f. The sparsity of g is the sparsity of f, or the number of monomials of f raised to the power log d. So in general, you can have quite a big blow up. The factors could be much denser. In fact, if you're just one variable, then you could have a polynomial with 2 monomials whose factor had d monomials. And so the question is this, can you think of polynomials which are worse than this, where the factors are much denser? So there was a conjecture from a long time ago that maybe this is essentially the worst possible blow up you could expect. If you had a polynomial f with polynomially many monomials, the factors could be at most this quasi polynomially denser than the sparsity of f itself. Seems reasonable. We don't have too many examples of polynomials with very dense factors. And in some sense, this is essentially the best we know. We don't know too many examples. But here is one slightly strange example which is even worse. So this doesn't work over all fields. Say we are over fp where p is prime, or p is the characteristic of the field, and your polynomial f looks like summation xi to the p. Then for any choice of d between 1 and p, this g of x is a factor of f of x. That's because when p is the characteristic of the field, summation xi to the p is the same as summation xi whole to the p. And because of that, g is a factor of f. And so when you look at this, f had only n monomials, but if you see how many monomials g has, if you expand this out and d is less than the characteristic of the field, g has roughly n to the d monomials, or n plus d minus 1, choose d. So g has roughly n to the d monomials, but f had n monomials. So g, the sparsity of g is the sparsity of f whole raised to d, as opposed to log d.
But is this fair? If I have x1 to the p, can't I write it as like x1 over 2 plus x1 to the p over 2 plus, like, I can add powers of p just like that and keep increasing the number of terms.
So I want the number of monomials. The sparsity is the number of non-zero monomials.
Yes, so I will have, like, suppose I want k sparsity, I'll take x1 over k plus x1 to the p over k plus x1 to the 2p over k plus x1 to the 3p over k and so on. And all of these terms are the same.
x1 to the 3p. No. So we would. I'm clubbing. Right. So you can cheat. I agree with. Oh, you mean you just have a monomial x and you have x to the p and you treat them two different.
Like that. Yeah.
Okay, so we club all that together. So I agree. So at least, so this is not doing that, right? I'm clubbing. I'm not. We have distinct monomials when
x1
we.
to the p is just x1. if P is the characteristic, I think.
Oh, good. Sorry. No, x1 to the p, x to the p, I'm not going to, good. It's not the same as x1 if functionally it is the same when you plug in values between 0 to the p. But as a polynomial, these are still different polynomials. I could plug in values to x1 which come from some extension, and so though on 0, on fp, they take the same values, but as polynomials, they are different polynomials. Okay. So when I'm asking this sparsity bound question, it's still a for me, x to the p minus x is a non-zero polynomial still.
Okay.
So with that definition of a polynomial, we can still ask the question. And so I agree. I mean, the earlier, when you think about the reals and characteristic 0, maybe all these issues don't arise. Over fp, you can play little games with the characteristic, and you can get much worse sparsity bounds. So if you're just counting the number of monomials, you can have these factors having many more monomials. Good. And here all the monomials, all the powers are between 1 and p. So we're not doing too many games of, the reason for the blow up is not that. Okay. Questions about this? Any other questions about this example? But basically the degree and the characteristic of the field that you're playing games with them, you can get worse examples. And this is basically the worst we know. The fact that the sparsity of G is a sparsity of f raised to D, we don't know any example worse than this. And so if this quantity D was big, D was n, then the factors of f could have exponentially more monomials than the number of monomials in f. You can't hope to say that sparse polynomials have sparse factors. But so there are two situations in which maybe you can say that. One is in characteristic 0 or in large characteristic, much larger than the degree of the underlying polynomial. It could still be that that first example was the worst. That the factors of a polynomial are only quasi-polynomially denser than the original polynomial itself. That could be true, and that would be very, very interesting to show. That over such fields, the factors of sparse polynomials are indeed sparse. That would be a very nice result. And another, and also very nice result, which I will talk about, is let's not think of D to be large. What happens if D is 5? If each variable has individual degrees, say 5, and your polynomial f is sparse, it could be that the factors are still exponentially dense, right? Because I mean, when individual degree is at most 5, you could still have 6 to the n many monomials. So in the case when D is small, when we don't think of D to be growing with n, can we still say something about the factors of sparse polynomials? So this is the case we will focus on. Let's bound the individual degree D. Let's think of D to be small. When D is large, in general, there's no hope of showing a good sparsity bound because of that last example. So let's think of D to be small and ask, is there any sparsity bound?
Individual degree just means the degree of that variable, not the degree of the monomial.
Not the degree of the monomial, but each variable has bounded degree. So if D is 5,
x to the 5,
you could have
x2 to the 5, but you can take product.
Right. You can have x1 to the 5 times x2 to the 5, so on and so forth. Yes. So this question had been looked at in the past. Pilka and Volkovich studied the case when D is 1. These are multilinear polynomials. And what can you say about the factors of multilinear polynomials? Sparse multilinear polynomials are sparse. This is fairly easy to show. And even when D is 2, it turns out to be not too hard to show. But D being 3 onwards, at least these proof techniques broke down. And so I won't talk too much about it. Rafael Oliveira, he was a student here some time ago. He also looked at the question of factors of sparse polynomials and factors of low polynomials computed by low depth circuits. He was able to show that factors of sparse polynomials, when D is again small, they have small depth 7 circuits. Something I'm not going to define, but this was looked at before. And Zev and Rafael also tried to study factors of sparse polynomials, and they had an approach to doing this which didn't materialize, but it motivated our work. which I will talk about. So what I showed in joint work with my student Vishwas, Bhargav and Ilya Volkovich is the following. We said that if F is an arbitrary field, okay, so it could be FP, this we are not able to distinguish between characteristic 0 and smaller and FP. So let F be an arbitrary field. That suppose you have any polynomial with S monomials and individual degree d, then every factor has sparsity at most S to the d square log n. Okay, so S to the d is inevitable by that example with the weird characteristic games. So you can't hope to get better than S to the d in general. And so what we are able to show is S, we get a bound of the form S to the d square log n. So for any d larger than 2, this is the first sub-exponential bound. And it doesn't look at the underlying field, and so it's somewhat tight because S, you can't do better than S to the d anyway. So the scope for improvement is that log n we don't know is necessary or not. I believe it's not necessary, the log n, and the d square might become a d. Okay, so that's something we show. And just to put this result in context of other previous work, closure results of this kind have been studied before. Are factors of low complexity polynomials, are they low complexity? So for us the complexity measure was sparsity, but in various settings this question has been asked. Beautiful work of Kaltofen from the 80s studied the complexity class VP, which is polynomials computed by small arithmetic circuits. And it was very, very surprising and beautiful work, and Kaltofen showed that if you have a polynomial computed by a small arithmetic circuit or a polynomial sized arithmetic circuit, its factors are also polynomial sized arithmetic circuits. And if you see it for the first time, there's no reason to expect such a result to be true, and it's I think it's a really beautiful result. Recently there was a self-contained simpler proof of the same result by these authors. I won't get time to talk about this. The work of Raphael, which I mentioned earlier, he showed that constant depth circuits of small individual degree, this is also closed under taking factors. The factors also look like constant depth circuits of small individual degree. Very recently there was a sequence of works showing such closure results for the complexity class VNP. Factors of polynomials in VNP are also in VNP. And some, this is more complicated to state, ADPs and formulas also have such closure results. And so what we are trying to show is, we are trying to study depth 2 circuits. So if you think about it, I haven't even defined what a depth 2 circuit is, but a sparse polynomial is a polynomial computed by a depth 2 circuit. And we want to show that polynomials computed by depth 2 circuits, the factors should also be simple. They should have low complexity, and at least in the case when the individual degree is bounded and up to a quasi polynomial blow up, we are able to show that polynomials, low complexity polynomials computed by depth 2 circuits have low complexity.
Also depth 2 or larger depth? The factors.
The factors are also depth 2 in this case, right? We're showing that sparse polynomials have sparse factors. So if a polynomial is computed by a depth 2 circuit, its factors are also computed by depth 2 circuits of not too large size. That's what, this is rephrasing the sparse polynomial result, because sparsity is captured by depth 2 circuits. And so that was the sparsity bound, that factors of sparse polynomials are somewhat sparse. And then we can also take our sparsity bound and convert it to an algorithm for computing the factors. So we show that if you have as input a sparse polynomial and you want to compute the factors of that polynomial, there is and the degree is at most d, so think of d to be say a constant, then you have a quasi polynomial time algorithm for computing the factors. Quasi polynomial time deterministic algorithm. If you are willing to do randomized, then Kaltofen has an algorithm, a randomized algorithm for computing the factors of general polynomials computed by small arithmetic circuits. So the main key point here is the fact that it's a deterministic algorithm. We don't know how to deterministically factor sparse polynomials, But at least now in the case when the individual degrees do, we have a deterministic quasi-polytime algorithm for factoring sparse polynomials. And if we got rid of the log n in the sparsity bound, we would get rid of the log n in the factoring algorithm. Okay, so the plan of the talk is the following. For the most part of the talk, I'm going to focus on the proof of the sparsity bound. And then whatever time is left, I'll tell you a little bit about factoring algorithms and give you a flavor of what goes into our factoring algorithm. Yes?
So for the last slide, there's a polynomial in size of the field. Is that the size of the field or the characteristic?
The characteristic of the field.
Okay.
This is, I put the size of the field here, but polynomial in the characteristic of the field is enough.
Okay. So if f is of characteristic 0, then it's just a constant?
Then yeah, it's just a constant. The complexity of the input would matter. How many bits are there in to represent the input polynomial, that would show up. Yeah. And this second factor is, it shows up even if you factor univariate polynomials, so which are inherently sparse, you still have that underlying term of polynomial in the characteristic of the field or the bit complexity of the input. So I'm ignoring that. Let's not focus on that term for now. Okay, good. So the main part of the talk will be the proof of the sparsity bound. So let's jump into the proof of the sparsity bound. So suppose you have three polynomials f, g and h, and f is equal to g times h. We want to show that if f is sparse with individual degree of each variable being d, then its factors are also sparse. They're at most s prime sparse, where s is at most, s prime is s to the o of d square log n. Right? That's what we're trying to show. What we will show is something slightly more general. So instead of saying if f is sparse, then its factors must be sparse, we'll show that if g is dense, then f must be dense. Okay, so and it's slightly more general for the following reason. We'll say if g is a so we'll show that if g is a polynomial of individual degree d with s monomials, and f is g times h. So g has at least s monomials, we need to show that f also has lots of monomials. So f, we'll show that f has at most has at least 1 over s to the d square log n monomials. So just rewritten the same thing. The reason it's slightly more general is that I'm not restricting the individual degree of f. I'm just saying g has small individual degree d. You multiply it with whatever polynomial h can have large degrees. So f can have large degrees. So no matter what polynomial h of unbounded degree you multiply it with to get an unbounded degree polynomial f, whatever you do, f needs to have at least 1 over s to the d square log n monomials. Yes, that's what we'll show. So in particular, if g has many monomials, there is no polynomial h that you can multiply it with and get a big huge cancellation of monomials. So that's what we're trying to show. The proof is going to be very non-algebraic. It's going to be convex geometry entirely. So here's the plan of the proof. So we'll take a polynomial f. It's a sum of monomials, and it's over an arbitrary field. Let's forget about the field. Let's forget about the coefficients of the monomials. Let's just care about the set of monomials in the polynomial. So each monomial has an exponent vector, right? So it looks like summation, some coefficient times x1 to the i1 times x to the i2, etc. Let's just keep that exponent vector, i1, i2, in, and do that for each monomial. So throw away all the information in the coefficient, in particular throw away all the underlying information in the field, just keep these exponent vectors and view them as points in R to the n. Okay, so our polynomial didn't have to be over the reals, but we don't care. The exponent vectors, view them as each exponent vector as a point in R to the n, so we got a subset of R to the n by the collection of exponents. And you look at all these exponent vectors, and now we define a polytope. You got a finite set of points in R to the n. Look at the polytope, which is the convex hull of these points. And this is a well-studied notion. It's the Newton polytope of the underlying polynomial. So the Newton polytope is just the convex hull of all the points in the support of this of f, which is the exponent vectors. So I look at this Newton polytope. So for example, if f is that polynomial, you discard all the coefficients. You only look at the exponent vectors, which is 0, 0, 2, 0, 0, 2 and 2, 2. And the Newton polytope is this polytope. It's the convex hull of the 4 exponent vectors. And let me tell you some nice properties. These are nice classical properties of Newton polytopes. I won't prove any of these, but they're a nice fun exercise in convex geometry or polytope geometry. Nothing fancy going on. These are all half page or few line proofs. 21? Yes, 21. This has been studied in 21. Yeah. Long, 98 years old. Yeah.
Newton was in what? 15. When was Newton?
No, it's in 2 years.
Newton. Yeah. Good. So f is g times, if f is g times h, then pf, the Newton polytope of pf, is the Minkowski sum of the Newton polytope of pg and the Newton polytope of ph. And what's the Minkowski sum? So if you have two polytopes or any two, I think it's two bodies in Rn, then you look at for every point in this body and you take any point in that body, you take their coordinate wise sum and you get another point. And you do this for every point here and every point here. You get the collection of all possible sums gives you another body. It turns out that if you have two polytopes, the Minkowski sum is also a polytope. Okay, so if you look at the Newton polytope of PF, it turns out to be the Minkowski sum of the Newton polytope of PG and PH. So that's a nice, elegant fact. It's not too hard to prove. So in order to prove this, you show that this one PF is contained in PG plus PH and PG plus PH is contained in PF. One direction is trivial and the other direction takes 2 lines of argument, but it's not hard. So good. So that's one nice fact about Newton polytopes. Here's another fun polytope fact. Again, not very hard to prove. So if you have any polytope P, let V of P be the set of corner points of the polytope or the vertices of the polytope. Then if you have two polytopes A and B and you take the Minkowski sum, you can't, the act of taking the Minkowski sum cannot shrink the number of vertices down. So if you look at the Minkowski sum A plus B, the number of vertices in A plus B is at least the number of vertices in A and at least the number of vertices in B. You can't cut down vertices by taking Minkowski sums. That's another fact which is again not very hard to prove. It's an easy exercise in polytope geometry.
Does this hold for all polytopes?
For all polytopes. Doesn't have to be a Newton polytope, but yeah, doesn't have to have integer coordinates or anything like that, arbitrary polytopes. And here's another easy trivial fact is that if you have a polynomial f, the sparsity of f is at least the number of corner points of its Newton polytope. And this is just trivial because the sparsity of f is the number of monomials. The Newton polytope was the convex hull of all the monomials, so the number of corner points is at most all the monomials. So this is just saying not saying anything. Okay, now when you put all these facts, 3 facts together, you get something nice. Okay, so the sparsity of f is at least the number of vertices in the Newton polytope of f. That was the trivial last property. But the Newton polytope of f is Pg plus Ph. And if you took the Minkowski sum of Pg and Ph, you can't shrink the number of vertices. So the number of vertices of Pg plus Ph is at least the number of vertices of Pg and at least the number of vertices of Ph. So this quantity is a lower bound on the sparsity of f, which is what we wanted to show. Like what we wanted to show is that if G is any polynomial with S monomials, and you multiply G with some polynomial h, arbitrary polynomial h, you can't shrink the number of monomials of f down too much. F has a reasonable number of monomials left. So what does the first line give you? So G is an arbitrary polynomial with S monomials when we want to show a lower bound on the sparsity of F. But this quantity is a lower bound on the sparsity of F. So it suffices to show a lower bound on this quantity. So it suffices to show that the number of vertices of PG, Newton polytope of G, is at least this quantity. Okay, so that's what we're going to show. In order to show a lower bound on the sparsity of F, we'll show that the Newton polytope of G has lots of corner points. Good. And I said that there was a work of Zev and Raphael which inspired our work. So there was this connection. So they had a different approach, but the connection between studying sparsity bounds and Newton polytopes was made in their work, and that inspired our work. Okay. Good. So we want to show, so we've reduced our problem to showing the following. If G is any polynomial of individual degree D with S monomials, then if you look at the Newton polytope of G, it has many corner points. Good. In general, if you have a polytope with many points, there's no reason to show this, hope for it to have many corner points, because for instance, here is a polytope with 4 corner points and some number of interior points, and here is another polytope with 4 corner points but potentially many more interior points. So we need to really exploit the bound on individual degree. Just by blowing up a polytope, you can increase the number of interior points and shrink down the number of corner points. So the bound on individual degree is going to be crucial in showing whatever we are going to show. And how do we exploit it? First, observe that in this statement, this G is a polynomial of individual degree. D is a bit of a distraction. I mean, what role is the polynomial even playing? We just cared about the exponent vectors of the polynomial in making this statement, right? So completely equivalent to this statement is the following statement. Let E be any subset of 0, 1, 2, 3 up to D whole to the power n, right? Because each exponent vector is a member of the set 0, 1, 2, 3 up to D to the power n. So let E be an arbitrary subset of size S of 0, 1, 2, 3 up to D to the power n. And what we want to show is that the convex hull of E has many vertices. It's an equivalent statement. We can forget about polynomial. It's completely, you have a set which is a subset of this lattice, and you want to say that the convex hull has many vertices. Okay, so that's what we want to show. And just reformulating with some notation, if given a set E, let V of E be the vertices of the convex hull of E. Right? Then I want to show that if E is any subset of 0, 1 of that lattice, then the total number of vertices is at most the number of corner points raised to D square log n. I'm just restating the same thing over and over again. So that's what we want to show now. We are reduced to showing this, that E, now we forget about polynomials, fields, everything, and factors. All we have to show is that if E is an arbitrary subset of 0, 1 up to D to the n, then the size of E is at most the number of corner points of the underlying polytope raised to D square log n. So the number of interior points is not too much as a function of the number of corner points. And the fact that we have to stay within this set 0, 1 to the D to the n means you can't take an arbitrary polytope and blow it up and get more interior points. Good. So let's try. So that's the statement we want to prove. Let's prove it. Okay. So proof. Okay. First, there's a classical result in convex geometry. It's called Caratheodory's theorem, which says that if a point is a convex combination of a whole bunch of other points, then it's a convex combination of at most n plus 1 of those points. So every element of E is a convex combination of at most n plus 1 elements of V of E by Caratheodory's theorem. So good, but E is not an arbitrary set. E is a special set. So here's a wishful thought. Maybe something stronger than Caratheodory's theorem is true, because our set is a special set. Maybe every point of E is not a convex combination of n plus 1 elements, but maybe it's a convex combination of much fewer points of V of E. Maybe it's a convex combination of at most d square log n points of V of E. Maybe. And maybe even more is true. Maybe it's not an arbitrary convex combination, maybe it's a uniform convex combination. And by uniform convex combination, I mean if a point, the coefficients of the convex combination are all the same. So it's the median or the geometric mean of whatever d square log n corner points. So that was a thought which arose while we were working on it, and we didn't know if it was true or not. And if you work with small examples, it feels quite true. It's hard to find examples where this is not true. And what we noticed was that if this was true, then we are done. And the reason we are done is the following. That's because you can get for every k tuple of corner points, you can associate it with at most one interior point. So you can get an injection from the number of interior points to k tuples of corner points, because every interior point is determined by some k corner points, and every subset of k corner points can determine at most one interior point, because every interior point was the convex combination of k points, and k points can determine in only one interior point because of this uniform convex combination thing. So if this wishful thought was true, then the number of interior points would be at most the corner points to the power k, and we would be done. So we were trying to prove this, and it wasn't long before we found a counterexample, so it wasn't true. Okay, so that was our wishful thought. Wishful thought is not true, but it turns out what is true is something very close to it is true. We couldn't show that every point equals a uniform convex combination of few points in the boundary, but we could show that every interior point is approximated by a uniform convex combination of few points on the boundary. And our notion of approximation is epsilon approximated in the L infinity norm, and think of epsilon to be 1/10. Okay, so and this is enough. This is true, and it turns out this is equally enough, because you can still get an injection from the number of interior points to k tuples on the boundary, because every interior point you can map it to the k tuple which approximates it. So and every k tuple can approximate at most one interior point, because a uniform convex combination of k points can't be close to two different lattice points. So here we are using the fact that E is a lattice. There's separation between any 2 points of E, and the L infinity distance is at least 1.
What is the counterexample that disproves the wishful thought?
It's not easy to give you bigger numbers, so I don't have it, but you have to play a little bit with it. Maybe you can construct it offline, but pardon?
Can you tell me the idea?
Just having a whole bunch of vectors, if we had zeros and ones and lots of them, and you add it up and you could cancel out, and I don't know. There wasn't a big planned out idea. Maybe some Hadamard matrix like thing with big cancellations. I'm not, yeah. It was just too ambitious to hope that was true. Yeah.
So what is the relation between this statement and this approximate Caratheodory theorem that you can always find some point within epsilon distance of, every point you want, you can find some point within epsilon neighborhood of it using log and other points in the vertex.
This is some other approximate Caratheodory you're talking about? If it's not L infinity, you mean L2 or something? LP? Yes. So good. So this is an approximate Caratheodory, the L infinity approximate Caratheodory I'm talking about here. And L2 approximate Caratheodory, I think, does not suffice for us here, because 2 points in our set, we know an L infinity separation and But
that's why you have log n, right? Because you want L infinity.
Right.
No, that's also on the usual topic.
Okay, so approximate Caratheodory theorems apparently have been studied for LP norms, L2 norms, and L infinity norms. The proofs, I think, in L2 and LP are much more complicated, but such theorems exist. What turned out to be, so this theorem I'm stating here is an L infinity Caratheodory, which turns out to be appropriate for this setting. And the proof is also just I'll give the full proof, it's a 3-line proof. I know that I wasn't say found out that there are, I googled for approximate Caratheodory and then I saw that there's a whole bunch of other approximate Caratheodories. And I don't know if there anything going to other norms will give anything better. I don't think they do, and they are more complicated. So I never had to worry about those. But this L infinity Caratheodory is an easy proof and just the right statement we need for this setting.
And then this level of abstraction is this tight or not?
This level of abstraction is?
This problem.
This statement? Is it tight? So good. I'll talk about that. I'll come back to that in a couple of slides. I think that's a great question.
So maybe the other approximation gives you smaller k.
It may give you better k. So that's a great question. That maybe you want to get better than d square log n for this question. Is this bound tight? We show that if e is an arbitrary set, then e is at most this to the d square log n. Is d square log n the right number? And using this approximate Caratheodory, we can show d square log n, but maybe you can show better. Maybe. So I'll also say that we know that we can't do much better, but maybe you can do better. I certainly don't know that this is tight. So good. So once you want an approximate Caratheodory and you can prove it, we googled for approximate Caratheodory, and one reference we found that was suited to us and which just fits our setting was a result by Barman in algorithmic game theory from 2015, which rephrased some lemma within the theorem was exactly this. But I don't believe this is the first reference for this. I think there should be earlier references for it. I just didn't know what was the correct reference, but this is one reference for this, and this paper didn't reference anything in the past. So let me just state what this result is, and the proof is really just 2-3 lines. So but I suspect this must be an older result. So V is any subset of points of L infinity norm at most D. Every element of V has L infinity norm at most D, which is our setting, right? Because all the elements of E were in 0, 1, 2, 3 up to D. So V is a subset with every entry has L infinity norm at most D. Then you take any mu in the convex span of V. There is another mu prime which is very close to it, which is epsilon close in the L infinity norm. And mu prime is the uniform convex combination of at most D square log n vectors of V. This is exactly what we wanted to show. So it's exactly what we wanted. And now instead of L infinity approximation, you can ask for L2 approximation and other approximations and do stuff with. And so there are other Caratheodory theorems which do that. Good. So that's all we need to prove, this approximate Caratheodory theorem which exists. But let me just tell you the proof because it's so simple. And when you see the proof of the result, it seems so wasteful that it feels like you should be able to improve it. So let me tell you more about that. But let's try to prove this approximate Caratheodory theorem. So I want to show that for every point in the convex span, there's a close by point which is a uniform convex combination of the corner points. And so let mu be any any point in the interior. So mu is a convex combination of at most n plus 1 of the corner points. That was Caratheodory. Right? So mu is a convex combination of n plus 1. So mu looks like summation ai vi. And you know that the ai's are non-negative and they sum to 1 because it's a convex combination. Good. Good. ai's are non-negative, they sum to 1. That sounds like a probability distribution. So let's treat the ai's as a probability distribution. They define a probability distribution on V1 through Vn plus 1. So where the probability of sampling from Vi is ai. So let's sample from this distribution. Let's take d square log n samples from this distribution. And let mu prime be their uniform convex combination. So that's it. Now I have a uniform convex combination of k points from the boundary. All I need to show is that this mu prime is close to mu in L infinity norm. So let's try to show that mu prime is close to mu. To show that mu prime is close to mu, I need to do it in the L infinity norm. I need to do it coordinate by coordinate. So let's just do one coordinate and then. So this is just easy Chernoff plus union bound. So a simple Chernoff union bound argument will tell you that for each coordinate, if you had for each individual coordinate, you didn't need the log n. If you just had 100 d square samples, it's just basic Chernoff will tell you that in a particular coordinate, you got close. epsilon close. And if you want to be close with high probability, that's what the log n is, why the log n is necessary, and then you union bound over all coordinates. And so you got the result. So this is like an easy exercise in Chernoff and union bound. And that's the proof. That's it.
So both the theorem and its proof were due to Moray in the 70s.
Due to who?
Moray.
Moray?
Moray, yes.
Okay.
They appear in a paper by GPCA called an unpublished theorem of Bernard-Moray.
I see.
This is usually where it's,
Okay.
how it's cited.
I see. Okay, okay,
Pretty
good.
much.
That's
So
good to
you
know.
can unify the L2 and L infinity. It's all the same.
Good.
Right, but in the L2 case, you don't get the log in. So
Oh, that's interesting.
Because you don't use Chernoff in.
Right, it's just the Hilbert test. Right.
But you still suffer d squared?
I don't usually phrase it this way, so you should have 1 over epsilon squared.
Yeah, so if you shrink
1 over
the
epsilon
points-
squared sparsity. So I'm assuming that the square on the d is because of 1 over epsilon squared. I don't
Right,
see
yeah,
where
the d
epsilon
square.
and d
So sorry, so epsilon could have been, so this should be epsilon d square over epsilon square. So what's changing is that the L infinity norm, if you knew that the L infinity norm of the v's was 1, so the 100 is hiding 1 over epsilon square. It should be d squared over epsilon square times log n.
So it's d squared, if you had the bound in the L2 norm of d, and you want to approximate in the L2 norm, you would get d squared over epsilon squared.
Good. But since we don't have, so the reason the L2 version of Chernoff of Caratheodory is not good for us is because we already have an L infinity bound on the v's. The L2 norm bound on the v's is pretty bad. And so we'd probably get a worse, if you apply the L2 Caratheodory, you'd probably get a worse bound because our input has this L infinity guarantee. And so to take advantage of that, the L infinity Caratheodory made more sense. So I don't think that going to the L2 Caratheodory would give something better, because yeah.
So Moray's theorem works for any type 2 metric, and this one, L infinity norm on dimension n, is type 2 of constant log n, and that's what we'll have to log n.
Okay, good. So I should ask you for that
Yeah, I will
reference.
send you that.
Okay, good. So
It's in French though, so.
so I wanted to look at it. Okay. Yeah. Yes.
Yeah, just want to make sure that I understand the statement. So here in the proof that you pick a random set of k points from this set V,
Yeah.
and then you show that in expectation the average of these k points is close to mu. And in the statement, is this mu prime a random point, or is this a fixed?
I just have to show that there exists a mu prime. So if you could show that it exists in expectation, that means it also there's some mu prime exists. I don't have to deterministically find it. I just need to show that such a point exists.
Right. So mu prime is the expectation of some random point, right?
Right.
But it doesn't mean that there exists a choice of from all possible choices of the random point that is close to the single point.
So the Chernoff bound will show you that with high probability, the mu prime you will get will be close. So the result of this Chernoff union bound, it won't be an expectation. It'll be a statement which says with high probability you will get a mu prime out of this random process, and that mu prime will be close. And if you can show that with high probability mu prime is close, means there is some mu prime which you can sample.
Yes. So maybe it's clear. So suppose V is the Boolean hypercubing n dimension. That's just the endpoints. Suppose you would like to approximate the point which is half in every coordinate.
Right.
It seems that you probably need every.
So you can get repetition. So when I sample from this distribution, this is sampling with repetition.
Okay.
So I think maybe that would solve your problem.
As it is.
Would it do that? This is sampling with repetition.
Oh, interesting. So it's like something over k are the coefficients.
Something over k, exactly. So you might sample. So you want 1 over k, but good, it's uniform, so it could be 2 over k's and 3 over k's, but then, yeah. Okay. So this is sampling with repetition, yes.
So, yeah, I just also want to confirm something. So I think this d square is inherent because if you shrink this grid so that it's a subset of 0, 1 to the n, I think 1 over d becomes the epsilon in Moray's lemma that he was mentioning.
Mm-hmm. So d square is inherent,
It's an
yeah.
infinity net of 1 over
Yes,
d.
yes, yes. So I think the d square is necessary to have this statement. So, good. So this completes the proof of the sparsity bound. So before I wrap up, so I think it's a really good question to ask, is this d square log n tight? Right, so this Chernoff and union bound seems wasteful. Did you have to do it in every coordinate? So one question is the d square log n tight? is the log n tight? First of all, maybe that log n was completely unnecessary. The log n was needed for the union bound in the Chernoff argument. And union bound is if you want to get it right on every single coordinate. Maybe it's enough to get it right on 99% of the coordinates. Maybe, I don't know. So we really hoped, yeah?
So the log n you definitely need, because if you could improve that, you would get a better algorithm for epsilon Nash. And, so subject to, like the ETH for PPAD, you can't get rid of the log n. But probably there's an explicit example, I just don't know.
Good. Okay, so great, because you've seen maybe this so the log n is necessary, so that's we do end up noticing. So at least the first reaction after seeing this proof was that maybe this log n is not necessary, maybe you can do better because it seemed wasteful doing this union bound. Why this Caratheodory, maybe there's some other Caratheodory, maybe there's some other argument, because why are we trying to approximate it in every coordinate? So we really hoped we could get rid of the log n, but then we were able to find examples where we show that the log n is necessary. So in this geometry statement, convex geometry statement, this statement. So you can ask what's the best bound? What can you say about E? Is the d square log n necessary? So I think we can show that the log n is necessary and the d square is necessary. I don't know d square times log n is necessary, but I think a d square is necessary and a log n is necessary.
But log n here being necessary is different from what Matt is saying.
I don't know if that's what he's saying.
Because, so what you were saying is that in the approximate version, log n is necessary, but this is a stronger statement.
That's true.
Okay, good. Maybe. So maybe in approximate Caratheodory, the log n is necessary. Good. So so maybe that's correct. So now back to this statement, which I think is a very nice, independent of sparse factoring, just as a convex geometry statement. I think this is it's a natural question to ask, that if you have a subset of the lattice, how many interior points can you get as a function of the number of corner points? And I don't have we can prove this, but I don't know what the right answer is. So we were hoping that log n is not necessary. So maybe but yes, we do show that in some sense it is necessary. So Ramprasad Saptarishi came up with one example for constant d, where he showed that where he came up with n points in 0, 1, 2 to the n with n to the log n interior points. It's again hard, it's non-intuitive, it's hard to come up with this example. We really believed it was not necessary, but then there exists a set of n points in 0, 1, 2 to the n with n to the log n interior points. It's a nice example.
But this does not translate to factoring.
It doesn't translate to factoring anything. This implies the factoring result. The factoring doesn't imply this. So you could, if you shave off the log n here, it would shave off the log n in the factoring. But it could be that this is tight, but still for the factoring result, the log n is not necessary. So that's a separate question. So separately, I was working with Avi also on this question, and I think we showed that the d square is also necessary, but d square times log n we don't know is necessary.
So can you say more about d square necessary is when n is very small, or no?
I think we can also show that d square plus log n is necessary, but d square times log n, but n is small. I think we can show d square plus log n.
Well, then it's very close.
It's very close, so we can't hope to improve. Another thing that we can show is that when E was of size n, when the number of vertices, we can show that n to the d square plus log n is necessary. Let me even say that. I don't know that v of E to the d square log n is necessary. If E was a large set, maybe you can do so. So I don't know the exact answer, but we know a lot. We know some stuff which shows that you can't improve it by much. So, but I don't know. I definitely don't know everything about this question. It's sort of what's the best bound. It's an interesting question for itself, and it's surprising that this easy proof technique gives so close to the right answer, and though I don't know it is the right answer. But unlike Gilad pointed out, this doesn't also tell you the right, doesn't just these tight examples for this geometry question don't translate to tight polynomials which have dense factors. Just because the log n was necessary in the geometry question, we don't have a polynomial whose factors have this log n in the exponent in the factor density. But so this is sparsity bound tight. So there's a geometry question which you can answer tightest, and there's also the maybe we lost too much in going to the geometry. from the polynomial question. This reduction to Newton polytopes where you forget everything about the field and you took out so little information. Maybe if you took out more information, you can get a better bound. So.
Are there fields for which it's tight? Like maybe
we don't know anything. I told you everything I know, basically. Yeah. So I have just maybe 5 minutes to 3 minutes left. So I won't tell you anything about the factoring algorithm, but I'll tell you let me just tell you a little bit about the context and then I'll stop. So the polynomial factoring problem is given as input a polynomial, find its factors, and it's a fundamental problem. And Kaltofen and Kaltofen-Traeger gave white box and black box randomized, very, very beautiful polynomial time factoring algorithms for when the input is a polynomial computed by a small arithmetic circuit. He gave beautiful randomized algorithms for computing the factors. And these factors are also small arithmetic circuits. Very beautiful, very highly non-trivial. And they're randomized, and it's a very interesting question, can you de-randomize it? And turns out there's a problem called polynomial identity testing, which is given as input an arithmetic circuit, decide whether the polynomial computed by it is identically 0, and that is also, we have beautiful easy randomized algorithms but nothing non-trivial and deterministic, and we believe it to be a doable but a really hard question to de-randomize it. And in joint work with Swastik and Amir, we showed that de-randomizing polynomial factoring is equivalent to de-randomizing PIT. So we also believe polynomial factoring, de-randomizing that to be a hard problem. But here's it's interesting to, but we know how to de-randomize polynomial identity testing for several classes of arithmetic circuits. So can we de-randomize factoring for those same classes of arithmetic circuits? So when the input polynomial is sparse, we know very efficient polynomial identity testing, deterministic polynomial identity testing, and that motivates can you do deterministic factoring also for this class. And so that's some background or context for our factoring algorithm. So we do for this when the input polynomial is sparse, we do get deterministic factoring algorithms. But again, the individual degree, we have a bound, that must be a small individual degree polynomial, and we have this quasi polynomial loss in the running time because of that log n which came from the sparsity bound.
So is it easy to see the connection between factoring polynomials and PIT? Or like what?
One direction is easier than the other direction.
So what's the easy direction?
If you can't even, I think if you can't even decide if a polynomial is 0 or not, how are you going to factor it? Maybe that's the easy direction. Okay. And but the hard direction is that if you can't, but the hard direction is that if you can do PIT, if you can do PIT, then you can factor. If you can do PIT deterministically, then you can factor deterministically. That's the harder direction to show. That if someone gave you an oracle which will solve PIT for you, can you use that to factor? That's the hard direction. Okay, so sketch of proof, so we go back to the Kaltofen algorithm for factoring, and there's a specific step which has randomness, which we needed to de-randomize, and which is project to a random space, and irreducible factors stay irreducible when you project to a random low dimensional space. We want to de-randomize that. We can't de-randomize it, but we do something else. We ensure that distinct irreducible polynomials which have GCD1 after this projection maintain the property of having GCD1. So that's something we do, and it turns out that suffices. So let's skip it. So that was a summary of the de-randomized algorithm. Happy to answer questions afterwards if anybody wants this. As a subroutine within it was given a factorization of a polynomial, test if the factorization is good, and that can be done using reconstruction algorithms for sparse polynomials. Maybe this is it'll get too heavy to go into it. So just summarize, we had a sparsity bound, we used it to de-randomize Kaltofen's factoring algorithm and get a de-randomized factoring algorithm for sparse polynomials. And just so, I think given what I talked about, the most interesting question is to improve the sparsity bound. And we talked a lot about that. If you can use the information in the underlying field, that would be fantastic, because I believe much stronger sparsity bounds are true. and getting for over characteristic 0 if you can show it for even large values of d. I think that's a really, really nice question. And the questions about factoring, deterministic factoring of sparse polynomials, also factoring other classes for which we know PIT. So sparse polynomials was one such class, but you can ask it for other classes. So I will end here. Thank you. And